So in this unit, we are trying to understand features and what types they may be. We shall explore binary features, binary feature geometries, and monovalent features because there are two different ways of encoding features. In the course of this discussion, we'll look first through an example through traffic lights and their various states to show how this may be modeled by in terms of a binary feature distinction and or a monovalent feature distinction formulation, and how this feature-based usage approach can be used to understand and model natural language. So the intuitive idea of features that we are appealing to can be grasped as the use of a parameter along which a contrast can be stated. Let's look at the instructions given by traffic lights, where their state and colors signify the following messages. A green signal, which steady signal, allows movement. A yellow signal prohibits movement and indicates a upcoming change of light. A red signal prohibits movement. A flashing red signal prohibits movement and indicates an upcoming change of signal. A green flashing signal allows movement and indicates an upcoming change of a signal. A yellow blinking signal allows movement and warns the driver about the presence of a unregulated or pedestrian crossing. And the order of signals is red, yellow, and green. But these signals all carry meanings, so that a responsible driver will recognize that a steady red signal indicates stop, don't move. A green signal indicates that the driver may go. Right? It also tells us that a red signal always, whether it is flashing or steady, always means stop, except that the flashing signal tells you that there's going to be it remains stop, but the signal is going to change. A yellow signal patterns with the red, except whether it also, unless it is blinking. When it is blinking, the driver may go, but then be careful. So now, in order to describe this contrast, which actually take red and yellow together and versus green, we need to be able to unify, we need to be able to come up with a feature geometry that unifies red and yellow in contrast to green, and also makes a difference between flashing and steady in contrast to blinking. There are two ways in which we may do so. One, we can use a binary feature geometry, where a plus or a minus, so features then are specified for either plus or minus. They indicate a binary opposition. That is, plus red means has the property red, minus red means that it does not have the property red, therefore it could be either green or yellow. So that is, when you assign a plus feature, you are saying that they are positively specified for the parameter concerned, and as this opposed to others which lack the parameter concern. Now the set that is denoted by the presence of the parameter is homogeneous, but the set that is denoted by the minus value, that is the absence of the parameter, is not homogeneous. So looking at the traffic lights example, an initial choice would be to set up the feature plus minus green and then associate it with the core functional meaning of stop and go. So plus G, which is green in form and has the meaning go. Minus green is red or yellow, or in fact could be blue, purple, pink or any other, and it has the meaning stop. However, this choice of feature cannot be correct, as it collapses the distinction between yellow and red completely. And we know that yellow can, depending on its state, sometimes mean go, because they do not have the identical function stop, yellow and red. So let's make a feature geometry. So that is, we think of the traffic signal colors as being denoted by not one but a subgroup of two binary features. Let's take these two features to be plus minus green and plus minus red. This yields the following meanings. When a light is plus green minus red, that means it is green in form and its meaning is go. When a feature is minus green plus red, it is red in form and its meaning is stop. When a feature is minus green minus red, then its meaning is yellow in form, and its meaning is maintain previous meaning. Plus green plus red would be any other color, brown, blue, pink, purple, etc. But this meaning is just not employed in the traffic signal system. Now let's build in the meanings of the states of the lights. If you recall, they can be in three states: steady, flashing, and blinking. Let's distinguish steady from flashing and blinking by the feature plus minus change of state. This is to capture the intuition that blinking and flashing both share the properties that during the event they denote there are intervals when the lights go on and off. That is, they exhibit change of states, whereas steady light does not. So let's let's also postulate another feature, which is plus minus on. Flashing is used to indicate light which is sometimes normally off, where blinking is something which is normally on. Assembling these feature geometries, we get the following values. Plus change of state plus on yields to a blinking form, and the meaning of it is caution. Plus change of state minus on leads to a flashing form, and its meaning is lights changing. Minus change of state plus on gives you the steady, and it has no independent meaning. Its meaning is the meaning indicated by plus G minus the plus minus G plus minus R. Minus change of state minus on means just off, right? That's the form. There are no lights at all, and it has no independent meaning. So if you combine the meanings of the two feature geometries, you get the traffic light system. When you have a steady green light, which means go, it actually encodes a set of feature geometries. The first is plus G minus R, and the second geometry is minus COS plus on. To get the meaning stop, which is a steady red, the feature geometry is minus G plus R minus COS plus on. To get the meaning of flashing red, which is stop, lights changing, you have minus G plus R as one feature geometry, which is an element of the set that denotes the meaning. The second geometry in that set is plus COS minus on. And this whole thing together means flashing red, means stop, lights changing. So when we use feature geometries, what we assume is that features do not necessarily map onto forms and functional meanings in a one-to-one fashion. They are organized into subgroups or constituents to do so. Nevertheless, even when we do this, we always assume that each feature does independently mark out a class of forms meaning. That is, the feature plus R independently marks out a class of items which includes all red items. Similarly, we may make the generalization that all items that bear a minus change of state feature do not have an independent functional meaning in this context. of traffic rules, with the result that only the meanings assigned to the colors of traffic lights contribute to the meaning of the whole utterance. Traffic lights may also be modeled using a system of monovalent or privative features. That is, the features that we are looking at don't have a plus or minus value, they have just a single value. They are also called univalent features. A univalent feature describes only those classes which are said to possess a particular parameter. There is no statement about the absence of the features. So in other words, they only express the monovalent value, the plus values of the binary features that we use. So using that system, we would describe the traffic light system as having the following feature system. G signifies green and it means go. R signifies red form and stop meaning. Y signifies yellow form and it's a maintain previous meaning. We could also then build in blinking and flashing in the light in the manner that we've done earlier. We could have the change of state feature and the on feature in a geometry, and this will yield to blink form and quotient meaning. Just a feature COS means that it's flashing, and it signifies lights changing. On, the feature on gives you steady in terms of form and has no independent meaning. Using a monovalent feature system, we could then build a feature geometry which would give you the same meanings as the traffic lights. So for example, the feature geometry G plus the feature on will mean steady green go. The feature red plus on will give you steady red meaning stop. G plus COS will mean flashing green go, lights changing. R plus COS would give you flashing red, stop, lights changing, and so on. It would seem then that a privative feature system would give identical results from a monovalent to a binary feature system. In a monovalent system or a privative feature system, you can also construct geometries, and the two approaches look virtually identical. Nevertheless, there is also an important contrast between the two approaches. While a binary feature system can represent both similarity and contrast, the privative feature notation cannot. So we had concluded that blink and flash were similar because they involved a change of state, a shared feature, and that they differed in the value on, but this is rendered opaque in a privative feature system. We can see that there is actually, in linguistic terms, there is a real and substantial difference in whether we use monovalent or binary systems. So recall that Yask defined the four main categories of words as nouns, verbs, prefixes, and particles. Remember that the distinction between nouns and verbs is based on an ontological distinction, right? Where a verb in this conception is one in which the notion of an event or a process is predominant, whereas a noun is one in which being an entity or being in a state is predominant. So let us assume then that we can say that both ontological categories are present in the definition of each category, and we could use binary features using a feature geometry or plus minus bhava and plus minus sattva. So then something which is plus bhava minus sattva is verb, something which is minus bhava and plus sattva is noun, something which is plus bhava plus sattva is a verbal noun, and the category minus bhava minus sattva, we do not know what it encodes, but it could in principle. It also has, to be able to get this, to get all the four categories, we could also have a feature geometry which uses a distinction between plus minus free and plus minus declinable, where we consider that preverb or prefixes, that is morphemes that appear in front of the verb, form a closed semantic unit in a fixed order. So then we could say that plus F, that is plus free, and minus D items, that is minus declinable, are particles and invariant words. Minus F, minus declinable items are prefixes and preverbs. And the other two categories, plus F plus D, and minus F plus D, do not exist. In short then, if we put these categories together, then we get a definition of what's a verb, a noun, a verbal noun, particles and invariant verbs, prefixes and preverbs, if we were to make feature geometries. So a verb is a plus, we can think of a verb is having the feature geometry of plus b, plus minus b, plus minus s, and a plus declinable feature as an independent feature and a plus f as an independent feature. A noun, on the other hand, is minus b plus s as a feature geometry plus a plus declinable feature and a plus free feature. A verbal noun is a plus b plus s category, which also has the features plus d and plus f. A minus b minus s feature geometry coupled together with a minus d feature and a plus f feature gives you particles and invariant verbs. A minus b minus s minus d and minus f collection of features gives you prefixes and preverbs. Now consider how these would be described in monovalent system. In a monovalent system, a verb would be have the features b, d and f. A noun would have the features s, d and f. A verbal noun would have the features d and f plus the feature geometry bs. Particles and invariant verbs would end up having just a feature f. But to describe prefixes and preverbs, we would have to set up an independent and new feature, bound. Now the distinction between the monovalent and the bivalent systems is that the monovalent systems do not involve any one single feature that distinguishes the categories, each category from the others, whereas the bivalent or the binary system does. So for the binary system, the values of the features d distinguish verbs and nouns and verbal nouns from the features, particles and invariant verbs and prefixes and preverbs. The feature plus f, which is plus minus, which is the feature plus f, which indicates something is free, distinguishes all other classes from prefixes and preverbs. The features, feature geometries plus minus b plus minus s group together particles and invariant verbs and prefixes and preverbs as distinct from the verbs, nouns and verbal nouns. So in terms of describing the whole system as variation along a set of parameters, is the binary system is much better. Okay. There have been fixes in the ways that monovalent systems can be input to certain non-variant interpretations that will enable us to get the effects of the binary system. So Adger 2010 develops a monovalent or privative feature system that makes the additional step of stating that the semantic and morphological interpretation of the absence of a feature would be interpreted as equivalent to an explicit statement of a feature of an opposing value. So it is what is implicit in the monovalent system is actually not the meaning of not that parameter value. This means that a statement that something is free necessarily means that it is not bound. Now that system becomes, through its rules of interpretations, equivalent to a binary feature statement, right? Because it makes all monovalent features as implicitly binary ones. This system, however, is not foolproof because it doesn't effectively give you the rules of interpretation that amount to the same thing as a binary system. Consider the statement that in the monovalent system that particles and invariant words are just a feature free, and compare it to the way that the binary system does it. The binary system states particles and invariant verbs to be distinguished by the feature geometries minus b minus f, minus b minus s, minus d plus f. To be minus b minus s has the system that it is not a noun, it is not a verb, it is not a verbal noun. Minus d has the meaning that it cannot be declined. And plus free just tells you that it exists as a free form. In the monovalent system, on the other hand, this form would be concluded to be, would be defined as just plus free. So what are the features that we consider implicit? So in terms of an implicit binary, this just means that it is not free. However, in the binary system, there is a fuller specification of the semantic meaning / grammatical form of that predicate. In this course, we shall remain agnostic as to whether we will use a binary feature system or a monovalent system when it is for language descriptions. Because though ideally a monovalent feature system should be eschewed because clearest specification of meaning / form can be given to us by the binary system. Many linguists have actually advocated the use of mixed feature systems in which some feature categories have binary specification and some are monovalently stated. For our mainly descriptive tasks, either will suffice. But for theoretical models, it is quite possible that we need to choose to systematically employ either one or the other, or a principled basis for determining which features must be binary and which may be stated monovalently.